Hello. Today we're going to take a look at arc measure. And of course, in mathematics, the first thing we have to do is define our terms and label them. Minor arc. That's this curve here. It's the part of the circle that goes from this radius to this radius and forms an angle. I drew one in that's about 75 degrees. I could be wrong. Maybe it's 80. The measure of this arc would be listed as, that's arc AB, would be listed as 75 degrees. And AB is the label we give to the small arc here, also called the minor arc. And then we put a little arc symbol over it. It's pretty graphic to indicate that we're talking about the arc AB, not, I'll say, the segment AB or the ray AB, etc., etc. What about, since the arc is really just the section of a circle, in this class anyway, which connects 2 points on the circle, later on you will find a broader definition of arc which applies to a segment of any curve. But right now we're just going to talk about arcs as they apply to circles. We also have an arc over here. After all, this great big part of the circle connects these 2 points also. It just connects them in a different way. For instance, if we went clockwise from A, well, then we subtend this minor arc of 75 degrees. If we went counterclockwise from A, we'd subtend a 360 minus 75. What's that, 285, I think? Yeah, let's take a look here. 285. Remember, that's not an 8, cheapers. There we go. The major arc is going to be 360 minus whatever the minor arc is, because all the way around is 360. So 285 plus 75, let's see what we get here. Are we close? 063. Oh, okay. Then this whole thing would be 285. Well, the measure. If I'm going to, I have to do it this way. This is the arc, just like with segments. And then this is the measure of the arc. And the measure of the major arc would be major arc, cheapers, would be 285, and the measure, that's M, of the minor arc. And the angle formed by the minor arc, that's called the central angle. That equals 75 degrees. This is really very simple. In this section, we're not even going to worry about, right now, we're not going to develop any theorems or anything about how long this actually is. We're only defining it in terms of degrees. But I think it's kind of obvious, just like with a circle. How far is it around the circle? Well, it gets farther around as the radius gets bigger, doesn't it? Same thing's going to happen when we get around to actually computing the length of this. The bigger the radius for a given angle, the larger will be the length of this arc. But for now, let's just talk about arcs in terms of their degree measure. The angle which they subtend, in other words. One more very simple thing to know about arcs. What about this arc here? AD. That's also a legitimate arc. I can draw another radius out here to produce the angle, and I'm going to say this is about 135. Now I'm just eyeballing it. I don't really know what it is. Let's just pretend that it's 135. That's the measure of arc AD. Actually, I should probably call this arc dA, even though when you just list two endpoints, you're always referring to the smaller one, the less than 180 part. The other part, in other words, the minor arc. The major arc, you would normally use 3 letters, just like this one here. Well, there's one outside the minor arc, so that you can tell what you're talking about. Because A, B this way, or go A, B around that way. Now you've got some ambiguity. So for the major arc, I would say include a third point. Put it on the circle and make it totally clear that you're talking about the long way around, not this one. So in continuing with our, in this case, labeling them all clockwise, from D to A to B, like that. So the measure of dA equals 135. So what would be the measure of, well, now this is a major arc from D to B, isn't it? If I were to write dB, you would think I was talking about this arc, and you'd be right. In the absence of any information, you assume the minor arc. So what I have to do is write DAB for this big arc from D all the way to B, also called the major arc. And that shouldn't be too hard to remember. The small one is the minor arc, the big one is the major arc. It's kind of graphic. Well, what would this be? Well, guess what? It's the measure of dA plus the measure of dB. In other words, we add up the degree arc measure exactly the same way we would add up the angle measure. If we were to add these two angles, it would be 135 plus 75. Well, no big surprise. It's exactly the same thing for the arc. And if you think about it, what else could it be? I think that's right. If we didn't do it this way, then this part wouldn't make any sense, would it? Because if this didn't turn out to be 210, this wouldn't be what it is, which is, I think, 150. This whole thing here is, say, 150 degrees. Well, if we don't know what these two are separately, all we know is this big major, it's the major arc of dB. dB would be the smaller arc, and we measure it. Well, what's left over after we subtract dB from 360 is this. And that will also turn out to be 210 if this is 150. In here, the measure. And I should put degrees on there. 150 degrees, 135 degrees. This is what's, this whole thing is what's left over, which is 210, but it is also happens to be the sum of these two arcs. And that's our arc addition postulate. As long as we put them end to end, the measure of the additive arcs, I don't think that's the right way to say it. The measure of the arc, which results from adding arcs together, is just the sum of the degrees of those arcs, or the sum of the measures of those arcs. So I could have written that the measure of DAB equals the measure of, doggone it, gotta quit writing things backwards, dA plus the measure of AB. And this is a very sloppy rendition of what's called our arc addition postulate. If you want to know what the arc measure is of an arc which is created by putting two arcs together end to end, you add them up. And I bet that's exactly what you expected it to be. And you're right. Like I said, this is going to be an easy section. And let's work some problems and see how easy they are. Now there's a nice one. QS is a diameter. which arc represents a semicircle. Let's see what we got here. This right here is the diameter. Let's mark it off with that. Make sure we don't get confused. Well, make sure I don't get confused. What about QR? That's this arc here. Doesn't look like a semicircle to me. Remember, a semicircle is just a half circle. What about B? RQT. RQT kind of looks like half a circle, but they didn't tell us that RT is a diameter, and this may not be an actual straight line. So we don't have any way of knowing for sure that RQT is a semicircle. Kind of looks like it, but we don't have any way of knowing that it is. How about QRS? Well, let's see, that goes from one end of the diameter past R to the other end of the diameter. Certainly looks like a semicircle to me. Let's check the other one, QRT. Well, since they've included this, that means we're supposed to go around this way. Not that it would matter much. If they just wrote QT, that would be this arc right here, which is definitely not a semicircle. QRT, well, that's this big one all the way around here. That's too big for a semicircle. It's like 3/4 of a circle and then some. So we're right back here. It must have been this one. QRS, this is the semicircle. And in fact, the endpoints of a diameter will always subtend a semicircle. For instance, if we said QS, well, first place we wouldn't really know which arc we were talking about, this one or this one, but the measure would be identical. They're both 180 degrees, and they're both a semicircle. Well, here we are in a section on arc measure, talking about congruent circles. Remember, from previous sessions, congruent circles are about as simple as you can get. The only thing you can check, the circle only has one measure. It's kind of like a square. Once you know the length of a side of a square, you know everything there is to know about that square. That's all there is to it. With the circle, all you need is the radius. And that's as much as you can have, actually. I mean, knowing more than the radius doesn't accomplish anything. You could be given the radius, the diameter, and the circumference, but the last two would be superfluous. The radius determines the diameter and the circumference. So the radius is the only thing, really, the only measure of a circle. Two circles with the same radii have to be congruent. If they don't have the same radii, they're not congruent. Well, here we have our old friends, Inseam and Fleabite, who claim that you can't tell if they're congruent because nobody told you if the radii are congruent or equal. Remember, radius is used to refer to the actual segment, which is a radius, and it also refers to the measure of that segment. So it would actually make sense to say that they didn't tell us if the radii are equal. But in a sense, maybe they did. Let's take a look. I'm going to draw these two circles separately and see if that makes any difference. Well, what we're going to do only works if we know that C and D are centers of the respective circles. But they're labeled as circle C and circle D, and that's how we label a circle, by its center. So by definition, C is the center of this circle, and D is the center of this circle. That's why this works. Now D is on circle C. If I draw the radius from the center of circle C to D, I'm going to draw out a radius. I wonder if I can do that. It's short enough. Well, okay, pretend that's a straight line if you don't mind. Over here, I've got center D, and C is actually on the circumference. Now, CD, these are the same segment. And, we already know from the reflexive property that a segment has to be congruent to itself. So, these two radii are in fact equal. So the circles are congruent. That works because of the way we label things. We know that these are the centers of the circles. If we had drawn this differently, for instance, if this is circle C and this is circle D, and then we have Q and R on their circumference of these two circles, we can't say that they are congruent because they both have the same radius. We can't say that at all, because the center of the circle is over here at D, and the center of this circle is over here at C. So to say that we can go from Q to R and call that the radius, which is the same for both of them, well, no, that's just nonsense. These overlapping circles, we can say that this is the same, this radius is the same for both of them, because this is the center of one circle and this is the center of the other circle. This line goes from the center of this circle to the circumference of this one, and it also goes from the center of this circle to the circumference of this circle. Ordinarily, you can't just overlap two circles and say, connect these 2 points and then say, well, that's the radius, so they're congruent. No, that's it has to be, you have to know that the center of one circle lies on the circumference of the other circle. In fact, that's kind of the salient point in this. You get the circumference of one circle lying on the center of the other, you're definitely in the right ballpark. Just for fun, I drew two circles with different radii. I want to see if it's possible for this to happen. Is there some way we can push these together so that the center of one circle lies on the circumference of the other? If we could do that with two non-congruent circles, then this problem really wouldn't make too much sense, would it? So let's see what happens. I can put the center on this circle here, but wherever I put it, it doesn't really matter. I'm not going to be able to get the circumference of circle D to pass through the center of circle C. Or if I do, I will not be able to get this center of circle D onto the circumference of circle C. The only way I can make this happen is if I start extending these, and of course turning it into an oblong is cheating. It has to actually be a circle. Well, it's kind of like a circle. Now, they both touch, and if I had drawn it correctly, I could superimpose one on top of the other. I wonder if I can do that, and then show. Oops. There. Well, you can see part of the problem. I put one circle right on top of the other, and yet notice the centers don't quite match up. That's just because of the way I drew it. But if I do that, now I can take and put it so that the center of one circle is on the circumference of another. And however I do this, I can pretty much get it if I had drawn a really good circle and I had drawn the centers accurately. Hopefully you get the idea here. And if these circles don't match up, there's no way you can get the center of one onto the circumference of the other. And then vice versa. You can get one to work, but you can't get both of them. For instance, if I shrink this down, now I can get the center of D onto the circumference of C. I can get the center of C onto the circumference of D, but I can't make both happen. Well, here's one where they give you the circle and the radius. You just draw it right in. It's the radius of 3. So PA and PB are both 3. And what they're doing here is trying to make you forget about the Pythagoras theorem. They tell you that this arc has a measure of 90 degrees. That means these two lines intersect at 90 degrees. We have a right triangle. AB is the hypotenuse. So AB would be I think we're looking for the length of AB. In this case, I'd write it as the measure of AB to make it totally clear that we're talking about the length of this segment, not the arc. I believe that's what they asked for. Yeah, see, they drew the little segment symbol up on top. So the measure of AB, also written as AB. But like I said, if I just write AB, maybe you would think I was talking about the length of the arc here, which I'm not. Anyway, that's 3 squared plus 3 squared, right? Well, not quite. That squared and squared would be 3 squared plus 3 squared, or 9 plus 9 equals 18. AB would have to be the square root of 18. Well, that's 2 times 9, right? Or 3 times the square root of 2. Oh, that's right here. Well, I guess we'll go with this one, won't we? 3 times the square root of 2. Or, you could remember one of your old formulas from an isosceles right triangle. It's always going to be the square root of 2 times the length of the side, if the two sides are equal. And that's pretty simple, really, to see, because what you're going to get, if, say, this was L and this was L, you'd have L squared plus L squared. That's 2L squared. When you take the square root of 2L squared, what are you going to get? You're going to get the square root of 2 times L. That's always going to be true. And that's why we got the square root of 2 times 3. You've seen that before, but reminder doesn't hurt. Well, here's one that looks kind of, well, messy. Lots of curves and lines and points all over the place. Well, let's see what they're telling us here. We got 2 circles, circle P and circle Q. P is the large one. And they're giving it to us that PQ is perpendicular to AB. Frankly, I don't think we needed to know that. I think we can solve this problem without knowing that, but I could be wrong. Let's take a look at what else we've got here. QA is tangent to circle P. That's the line from the center of the circle to A here. Well, remember from a previous section, like the last one, the two tangents drawn from a point outside the circle to the circle have to be congruent. So QA and QB are the same. I should just write that out. AQ is congruent to QB. That's these two. Well, PA is a radius and PB is a radius. That means that they're congruent also, which means we have a kite. We have 2 adjacent sides are congruent here. These 2 adjacent sides are congruent. So we have a kite. And for a kite, we already know that the diagonals are perpendicular, so they really didn't need to tell us this. I would say that was superfluous, but maybe they had something else in mind. I would say they're smarter than I am, so if they included it, it must have been a good idea. Well, radii and tangents are perpendicular. That means this angle here, PAQ, we could call it. In fact, let's call it that. PAQ, that's 90 degrees. PBQ, that's 90 degrees. What do the interior angles of a quadrilateral add up to? And that includes a kite. Anything with 4 sides is a quadrilateral. They add up to 360. Well, we got 180 of them accounted for already. 90 here and 90 here. That means there's 180 of them left over, and 60 of them are devoted to this little angle here. What's 180 minus 60? 120. So if the angle here is 120, that's how we measure the arc, isn't it? So this arc, this larger one here, is 120 degrees. And that's the measure of AUB. AUB, that's this here. So all we had to do really was remember our properties of kites and quadrilaterals. First we had to recognize that what we had here was a kite. Remember a kite is a quadrilateral. Remember that radii and tangents are always perpendicular. Put it all together and it's actually a very easy problem, isn't it? Not very challenging really. And the answer, if you're wondering, was 120 degrees. I didn't make that clear. That's the measure of this larger angle, which is of course the measure of the arc, which subtends that angle. Now here's a pretty long, boring problem. Hope you slept well last night. Oh, it's not really that bad. There's a lot of questions here, but we'll take them one step at a time. Hopefully they'll be kind of simple. What we have is a surveillance camera. That's this right here. And it's rotating from A to B and then back again. First question, what is the measure of this arc? Well, they tell us that these walls are perpendicular. It's a good way for a wall to be. If this minor arc here was 90 degrees, remember the major arc is 360 minus the measure of the minor arc, or in this case 360 minus 90, which is 270. So that wasn't too tough. That's 270. How long does it take the camera to survey the entire area once? Aha. Well, 10 degrees per minute. That's a rotational speed. The speed of rotation, just like now your engine, you might have a tachometer if you drive, or maybe you have a friend with a car with a tachometer. Gives you revolutions per minute. That's rotational velocity or speed. This is rotational speed, 10 degrees per minute. Well, this is super easy because it would be easier if I left myself room, wouldn't it? All I have to figure out is how many 10 degree sections are there in 270 degrees. Because we already have our arc addition postulate, which tells us that we can just add everything up the way we'd like to. So if we do that, we get 27 of those little sections. 27 10-degree segments here, or 27 10-degree arcs. To subtend 27 10-degree arcs at 1 minute per arc is going to be 27 minutes, isn't it? So we can go ahead and write that in. Okay. Wow. That's kind of weird when you think about it. Oh well. Maybe if it went faster, it'd be hard to keep track of what was going on. It might make you dizzy. But it does seem to me that if it takes that long to go from here to here, well, once the camera was here, you got nearly half an hour to do anything you want over here. Doesn't seem very secure to me. Oh well. If the camera's at an angle of 85 degrees from wall B, this is wall B right here, and it's slightly less than 90 degrees, right? If we extend this line, that would be 90, so it must be like right down here somewhere. Pointing at this point, this spot right here, I would say. And rotating counterclockwise, which is that direction. I'll put an arrow on there. Boom. That's counterclockwise. How long will it take for the camera to return to the same position? Well, that's going to be one cycle. And it seems to me, let's take a look and see what happens. This is 85 degrees, so what he has left to subtend here is 270 minus 85. Let's put that over here. $1.85. I think that works. Yeah, 17. That works. Now, if it's going to go there and back, it's going to actually have to subtend 2 times 185, or I could just add 185 to it, couldn't I? And you get 0, 7, 3. Go 85 degrees that way. That sure doesn't seem right to me. Hang on. Pardon me, I'm so dumb I forgot what I was doing. This is the 85 part, which we don't care about. This is the 185, and we have to go this way 185 degrees, and then back 185 degrees, and that would be 370 degrees, which when you divide by 10 should give you 37 minutes. I know when I do these problems it looks like it's really easy to get confused. I just make it look easy to get confused. Sometimes we use those little marks up on the upper right. I forget what they're called. Kind of like apostrophes. We do the same thing with inches. In inches and minutes, frequently use both of these. You get hours, minutes, seconds. I think double marks is, maybe double is seconds. Tell you what, maybe I just forget those. Let's do it this way. Minutes. There. No ambiguity. 37 minutes. 27 minutes to go from A to B. In fact, now that if you look at it that way, that's even worse. Suppose the camera was right here and going that way. Well, that would be more than 37 minutes. You'd have close to 40 minutes if you were right here once the camera got to here, before the camera would ever get back to see what you were doing. I don't know how fast the average criminal is, but I suspect a motivated criminal could get a lot done in 40 minutes. Maybe I'm wrong. What about the last one here? The camera is rotating counterclockwise, and it's 50 degrees from wall A. Well, let's see here. That's about half of a 90-degree angle, so call that 50 degrees from wall A. It's going counterclockwise, so now it's going the opposite direction. After 50 minutes, where would it be? Well, that's not too tough. It's 10 degrees per minute, so it will travel from 50 plus 15 times 10, which is 150. That's 200 degrees. Well, once again, I've misread something here. I thought they were doing this problem the opposite of the previous one, but they're not. It's 50 degrees from wall A, and it's still going counterclockwise, which makes total sense, actually, I guess. If it goes counterclockwise, it's going to go 50 degrees this way, stop, and then start going the other way. So this, forget it. When it gets to wall A here, it's going to change direction and start going back the other way. So if it's right here and going counterclockwise, it's going to go 50 degrees to here. Well, that's 5 minutes, right? So that's 5 minutes to wall A. Now it changes direction and starts going this way for another 10 minutes, which at 10 degrees per minute, well, 10 times 10, that's 100. So it comes 100 degrees away. From wall A. It should end up, let's see, that's 90, right about here. After 50 minutes, that would happen. What would happen? 5 minutes this way, and then 10 minutes traveling 100 degrees this way. Sorry about the mistake. I hope when you guys watch me do this, you realize how important it is to pay close attention to every word in the problem and not start making assumptions like I do, and then having to do the problem all over again. Because obviously you'll lose time on tests when you make the kind of dumb mistakes I do. But if you watch me make dumb mistakes, maybe you'll learn not to. I hope so. Remember, it's good to learn from your mistakes. It's better to learn from someone else's. Here we have one referring to a clock, which makes sense. Most clocks are in circles. Oddly enough, even digital clocks tend to be in circles. Doesn't make much sense. They're going to ask us to figure out the measure of the arc formed by two hands of the clock after a certain amount of time has gone by. In this case, 20 minutes. Now, their starting position at 1 p.m. will be minute hand pointed straight up and the hour hand pointed out here at 1. How many degrees is it from, say, 12 to 1 or 1 to 2? Each of the major marks on the clock from 1 to 12. Well, there are 12 of those sections, so I would say that it's 360 divided by 12, which is, of course, 30, meaning that it's 30 degrees for each of these hour markers. So we go from 12 would actually be up here. I wrote 0 here because this is 0 degrees. I'm going to call straight up 0 degrees. Just easier. So how far is this minute hand going to move in 20 minutes? Well, it goes to 1, 2, 3, and then 4. Now, I can't say much for my scale here. I think it's a bit off, but that's okay. This is mostly going to be algebra. So this one went from 0 to 4 times 30 degrees. That would be 120 degrees. 4. That's how far the minute hand moved. It went from 0 to 120. What about the hour hand? What's it going to do? It has to keep moving, because all the way around in 1 hour it's going to go from 1 to 2, and that would be 30 degrees. In a third of an hour, where is it going to go? It's going to move 1/3 of 30 degrees, or 10 degrees. It was already at the 30 degree mark, so it went from 30 to 40. Maybe I should go ahead and draw that. So we see the minute hand started at 0. Little one started at 30. Now this little one is at 40. And this one is at 120. So the arc in between here would be 80 degrees. Well, that's the angle in between is 80 degrees, which is the same as the measure of this arc, which now exists between the minute hand and the hour hand. The only thing about this problem is you had to recognize the fact that the hour hands also move. And of course, this is not to scale. I mean, if this is 30 degrees, that doesn't look much like 10 degrees, does it? I should have drawn this a lot closer to this one, but you start smashing things up together, it's hard to see what's going on. This is a little bit distorted scale-wise. But the important thing is the hour had to move 1/3 of the distance from 1 to 2, which would be 10 degrees. Otherwise, the answer would be 90. So, right here, we've got 80 degrees. What about this one? At what time before 2 p.m. to the nearest minute will the hour and minute hands form a diameter? Meaning that the angle between the hour hand and the minute hand has to be 180 degrees. When would that happen? Well, that's going to be kind of a tough problem, isn't it? Well, this looks like a case for rotational velocity, which is, in this case, is fairly easy to compute, isn't it? In 1 minute, how far will the minute hand travel? Well, each of these marks is broken up into 5 minutes, so it would be 1/5 of the 30 degrees that goes from 12 to 1. 6 degrees. So let's call it the long hand and say h sub l. Yeah, why not? What the heck? H sub l. The speed for hand h sub l is, we write it as v for velocity. Rotational velocity equals how many degrees? 6 degrees per minute. Oh, okay. What about the hour hand? It's going to be quite a bit slower, I hope. It's going to move 30 degrees. Let's do it over here. 30 degrees in 60 minutes. So the speed is 0.5 degrees per minute. And what we're going to have is, after a certain number of minutes, we'll say x, x times 6 degrees, and let's start at 220. What the heck? So at 220, the big hand right here is already at 120 degrees. So we have 120 plus the number of minutes that have elapsed times 6 degrees, and that will give us the degree position anywhere along this clock or circle. And for this one, well, that's at 40 degrees. And it moves 0.5 degrees for every minute. So this is going to be moving much faster than this, so this angle is going to get larger as time goes by. No, I'm not going to break into song. Now, what we're looking for is the point where the difference between these two angles equals 180 degrees, which means I would subtract this, which is going to be the smaller angle for sure, from this. So if I wrote it like that, boom, I'd have an equation, wouldn't I? And what happens is this has to equal 180. So we have to find x. So let's give ourselves a little room and do that. We've got 120. So we just set up our equation here. We've got 120 plus 6 times x. X is the number of minutes, which we don't know yet. That's minute hand right here is already at 120 plus some number of minutes is going to form a 180 degree angle with the minute hand, which is also moving, which is why we have to incorporate both into our equation. This one starts out at 40, and we subtract the position of the hour hand from the position of the minute hand, and get that 5.5x equals 100. that means that 18.2 minutes have elapsed for the minute hand and hour hand to just form a straight line. In other words, this one will have come around enough, and this one will have moved this way enough that they form a perfectly straight line, and therefore a diameter. And they break the clock up into two semicircles. Well, we started at 120. And it took 18.2 minutes. So, we got 120 plus 18 minutes. I don't think you need a calculator for that. It would be 138.2 of a minute. That would be like 12 seconds, but they only asked us for the nearest minute. So at 138, these two should form, and that should form a straight line or a diameter, and that should be true for any clock. So take a look at a round clock sometimes at 138 and see if it actually, the minute and hour hands should form a straight line. Well, that's about it.